Dear students, I am going to start with one of the lesson of the second PUC syllabus, which is electric charges and fields. Now, what are electric charges? Every matter possesses a property called mass, and due to this mass, it exerts force on another mass. Due to mass of one body, it exerts force on another mass, and that force is called as the gravitational force. We call it as a gravitational force. Similarly, there is an intrinsic property called charge, and if there is another particle possessing same property, then this matter exerts force on the other, and that force is called as electrostatic force. So basically, charge is the property due to which it exerts a force on another particle having same property called charge, and that force is called electrostatic force. Mass, when we say, there is no positive or negative, but when it comes to charge, it is found that the charges are of basically two types. There are two types of charges. Which are those two types of charges? One is positive, the other is negative charges. So charges are of two types, positive or negative. And this sign convention of positive and negative was introduced by Benjamin Franklin. So Benjamin Franklin introduced that there are two types of charges. He classified charges into two categories. Now, what are the examples for these charges? So I am going to start with the positive charge. Positive charge. So example for positive charge is protons. Then we have alpha particle. Then we have positron. So these are example for positively charged particle. What about example for negative charge? Example for negative charge, electrons, and then there is something called beta negative particle. Beta negative particle. But is it mandatory to have charge in a particle? The answer is no, because there are particles without this property, and such properties are called electrically neutral particle. Example, neutron. In neutron there is no charge. Then we have photon. This is proton, this is photon. So neutron and photon are good example for electrically neutral particle, or we also call it as uncharged particle. And this electric charge is different from electric current. Electric current is measured in terms of ampere, whereas electric charge is measured in terms of SI unit, Coulomb, C-O-U-L-O-M-B, Coulomb. It's named after Augustine Coulomb, and the symbol for that is capital C. So capital C is the symbol used for electric charge, that is the SI unit. And they have asked this question in the examination in March 2014. This question has appeared for 1 mark. What is the SI unit of charge? And you have to write Coulomb as the answer. Now, I have told you there are example for positively charged particle, negatively charged particle, and all these charge which we can measure it because it's a physical quantity having SI unit Coulomb. So what is the charge on an electron, which is denoted by E? Charge on the electron is found to be equal to minus 1.6 into 10 to the power minus 19 Coulomb, and you have to remember this constant value. Okay, it's 1.6 into 10 to the power minus 19 Coulomb. Similarly, what is the charge on the proton? The symbol is the same. It's E only, which is plus 1.6 into 10 to the power minus 19 coulomb. That is the charge on the proton. Okay, E is equal to 1.6 into 10 to the power minus 19 coulomb positive, and the charge on the electron is minus 1.6 into 10 to the power minus 19 coulomb. And what is interesting here is their values are the same. Can you see that? They have the same values. Okay, but only difference is one is negative, other is a positive. And you also should remember the mass of the electron, which is 9.1 into 10 to the power minus 31 kg, whereas the mass of the proton is 1.67 into 10 to the power minus 27 kg. So they have different masses, but same magnitude of the charge. Same magnitude. Magnitude means only the value. Okay, but their signs are opposite. So this constant you need to remember from the exam point of view. Sometimes they'll give the value, sometimes they don't give the value, in which case you have to substitute these constant. Okay, so charge is a physical quantity having SI unit, which is coulomb. It is different from electric current. So electric charge and electric current are different. Electric charge is a derived quantity, whereas the electric current is a fundamental quantity. Now, what is the device used to measure this electric charge? To detect the presence of the charges, a device is used, and the name of the device is called electroscope. It's called gold leaf electroscope. Okay, the device looks something like this. So where there is a glass jar, so here there is a glass jar, and these are the very thin sheets of gold. That's why it is called gold leaf. It is as thin as a leaf. And then if you bring a charged body and if you place in contact with the disc, the charges flows to the gold leaf, and if the charge, since the charges are of same type, they get repel each other. So moment they repel each other, you can prove that the rod, which is brought, is charged. So that is how we can detect the presence of the charges using a device called electroscope. So what are the properties of the charges, the various properties? So this is an important question. So as you can see, it has appeared 3 times in the examination, and let's see one by one property. The first property, electric charge is additive. So what do you mean by charges are additive? Since it is a scalar, we can just add the charges. Let me take Q1 is equal to plus 1 coulomb. Q2, that is the second charge, minus 2 coulomb. Q3 is plus 4 coulomb. Now what is the net charge? You have to just add them algebraically. So Q is equal to Q1 plus Q2 plus Q3. Q1 is 1, Q2 is minus 2, and Q3 is 4. 4 plus 1, 5, 5 minus 2 is 3 coulomb. And what is the sign? It's a positive. So this is the meaning of the statement. They are additive. So you have to just add those charges together. Okay, all right. Property number 2, the charges are conserved. So we have already learned some of the law of conservation, law of conservation last year, like law of conservation of linear momentum, law of conservation of energy, law of conservation of angular momentum, in which we say that in a system, the total energy of the system remains constant, or total linear momentum of the system remains constant. Similarly, the charges are conserved. That is, in a closed system, the total charge remains constant. Here there is a body having charge plus 4 coulomb. Here there is a body having charge plus, or let me consider minus 2 coulomb. Okay. Now, what is the total charge of the system? Plus 4 minus 2 is minus 2 coulomb. Now, I am going to transfer 1 coulomb from here to here. Plus 1 is transferred. Okay. When it is transferred here, plus 4 has lost 1, so it becomes plus 3 coulomb. minus 2 plus 1, it has received 1, correct? No, plus 1 minus 2 is minus 1, correct? Now check, what is plus 3 minus 1? Plus 3 minus 1 is nothing but minus 2 coulomb only. Before transferring, it was minus 2. Even after transferring, it is minus 2 only. So that means the total charge of the system remains constant before and after transferring. And that's why we say that the charges are conserved. Charges are quantized. So charges are quantized means the total charge in a system is always integral multiple of the magnitude of the charge of the electron. Q is equal to plus or minus Ne. What is the least charge that can be transferred from one body to another body? That is, this is the least, 1e. That means the least charge that I can transfer is that of 1 electron. I cannot transfer half electron or 1/4 of the electron. We can't cut electron into parts and then we can transfer. What is the least that I can transfer? 1 electron. What is the next possibility? 2 electron. What is the next possibility? 3 electron. Next, 4 and so on. So in general, how much? N, where n is the integer. See, 1, 2, 3, 4. It has to be an integer. So, and that's what we have written. And this property is called as quantization of the charges. So what do you mean by quantization? The total charge on a body is always is equal to integral multiple of the charge of the electron. Why do we write positive and a negative? Because if I transfer, imagine 1 electron from one body to another. If I transfer 1 electron, okay, so let me give this example. So there are 6 protons and then 6 electrons are there, okay. And here also there are 6 protons and then 6 electrons are there. So right now 6 proton, that is plus 6e, and minus 6 electron, minus 6e. What is the net? It's a 0. Here also 6 proton, which is plus 6e minus 6e. What is the net? It's a 0. Net is 0 right now. Now I'm going to transfer 1 electron from here till here. 1 electron is transferred. So now once 1 electron is transferred, look at this here. It is a plus 6e. This has a lost an electron. It becomes a minus 5e. Whereas here plus 6e, it has received an electron. It becomes a minus 7e. So what is the net? Plus 6 minus 5 is nothing but plus 1. Plus 6 minus 7e, nothing but minus 1e. So the body which loses electron becomes positively charged. The body which gains electron becomes a negatively charged. So that's why we have written plus or minus. So that means a body can be either positively charged or it can be even negatively charged. So when a body becomes positively charged, when it loses electron. When it becomes negatively charged, when it gains electron. And that's why we write plus or minus e. So the total charge is always integral multiple of the charge of the electron. And that property is called the quantization. So that's why we say that the charges are quantized. Now based on this equation, I can always find the number of electrons that is to be transferred. How to do that? N is equal to Q by E. N is equal to Q by E. Just imagine that on a body, the total charge is 1 coulomb. The total charge is 1 coulomb. And value of E, we know it 1.6 into 10 to the power minus 19. And when you simplify this using the calculator, you will get N is equal to 6.25 into 10 to the power 18. Take the reciprocal and then simplify, you will get this value. 6.25 into 10 to the power 18. So what is this number? If you want to charge a body to 1 coulomb, then you have to transfer an electron of 6.25 into 10 to the power 18 electrons. If I carry 6.25 into 10 to the power 18 electrons in my hand, then I'm carrying a charge of magnitude 1 coulomb. And if it is an electron, then it is minus 1 coulomb. So, you need to remember this, the number of electrons to be transferred so that the charge on a body becomes 1 coulomb is 6.25 into 10 to the power 18. Now, what if the charge that I want to transfer is 1 microcoulomb? Then, to this number 6.25 into 10 to the power 18, multiply this 1 micro. Micro means how much? 10 to the power minus 6. So, you will get 6.25 into 10 to the power 18 minus 6 is 12. So, plus 12. So, like this, for any charge, I can find the number of electrons to be transferred. Okay. So, that's why you need to remember this, and we get this value from the quantization property. Property number 4, charge is a scalar quantity. So, that is why it is additive in nature. Okay. Right. So, 4 properties: electric charge is additive, charges are conserved, charges are quantized, and charge is a scalar quantity. So, do remember, it is a important either 2 marks or 3 marks question for the board exam. Okay. Right. Electrification. So, again a question from the examination. So, what is electrification? Electrification, method of charging a body is called as electrification. Method of charging a body is called as electrification. There are 3 methods by which one can charge a body. The first one is electrification by friction. In this method, you take 2 suitable bodies and just rub them against each other. And when you do that, the electrons are transferred from one body to another body. Electrons are transferred from one body to another body, and thereby one body becomes positively charged, other body becomes negatively charged. And this method is called as electrification by friction. The good example is that, if you take a plastic comb and then if you comb your hair. So, I can't try that. So, you try it, dry hair, dry comb and comb it like, okay, rigorously, fast. After that, place it near small pieces of paper, okay, and then you find that these papers get attracted. So, you can see that here, okay. See, there is a comb which is already combed, and then when placed, near a piece of paper, you will find that the pieces of paper get attracted. So, here the friction between the comb and the hair makes the comb as well as your hair charge, and due to which it is capable of attracting very small pieces of paper. So, that is method 1. Then what happens is, if you hold that comb, nearer tap water, okay, so it repels the path of the water, and so that the path of the water is get deviated like this. A charged comb is capable of bending the path of the water that you get to see in this particular image. Okay, right. So, that is method number 1. Method number 2, conduction. So, this method is used in the case of conductors only, where if I bring a charged conductor, okay, and then if I place that in contact with another charged sphere. So, this is the conductor, okay, conductor. This is the insulating stand, this is the ground. If I place one conductor in contact with the other, then the charges are transferred from one body to another body, okay. And human body is a conductor, earth is a conductor, all the metals are conductors. And that's the reason why you get to see here, correct. So, this is the charged sphere, and when the charged sphere is, when it is touched by the lady, the charges are get transferred to the hair, and then you can see how the hair stands, okay, right. Again, this experiment fails if I touch it, but for that you need not head, but you need hair on your head, okay, right. So, that is second method of conduction, and you get electric shock because of the conduction. The charges flows through your body, and that is how you will experience electric shock. Electric shock is nothing but again example for conduction of the charges, flow of the charges through your body, okay. The third method is called electrification by induction. In this method, we place a conductor, any charge, okay, positive or negative, nearer another conductor. We don't place them in contact. In conduction, we have to place the two bodies in contact. Only then flow of charges takes place. But here, we place the body nearer a conductor. And now what happens is these positive charges attracts all the electrons like this, one side. Of course, positive, because we call this as unlike charges. So unlike charges, they attract each other. And once the electron they move to the other side, so this end becomes a shortage of electron. So that's why we draw them positive. And now what you have to do is, you take a wire and connect this end to the ground. And when you connect this to the ground, all the electrons from the ground, they go to the conductor through this wire. Electron is negative. These are positive. So they get neutralized. When plus 1E combines with minus 1E, it becomes a 0. That is, this end is get neutralized now. Clear? Now you remove the wire and then take this body away. Now you can see what remains on the conductor, only negative charges. So this is the method by which you can charge a body. That's called third method of induction. So you do remember the heading explanation is not required. So what are the three methods? Method of friction, method of conduction, and method of induction. Okay. When a body is charged, especially the conductors, what do you mean by charging? Either losing electrons or gaining electrons. If they gain electron, then those electrons will reside on the surface of the conductor. They will not remain inside, on the surface of the conductor. If it loses electron, then deficit of electron on the surface is represented by positive charge. Writing positive charge doesn't mean that the protons will come and stay over the surface. No. Surface is a shortage of electron. So this is negatively charged body. This is positively charged body. And if I just draw a circle, it's an electrically neutral body. So this is the meaning of the diagram that we draw. Negatively charged body, positively charged body. Now whenever body is a charge, either positively or negatively, the charges will reside on the surface of the conductor, whereas in the case of insulator, they remain even inside also. So how the charges get distributed? The distribution of the charge, it depends on the shape of the body or shape of the conductor. In the case of sphere, the distribution is uniform throughout the sphere. Whereas if it is an irregular shape, the charges are concentrated more where the curvature is more, where there is sharp edges or sharp points. And that's what you get to see in the next diagram. You can see the charges are more concentrated here because there is more curvature, more bending, more sharpness. Suppose if I take a rectangle, and if I charge that, then the charges are get accumulated here more because it's a sharp end. So at the sharp points, you get to see more charges. Here, there's no sharp edges, it's a uniform. So that's why the distribution is uniform. Okay. Now once the charges are get distributed, we can always calculate the concentration of the charges using a quantity called density of charge. Depending on the shape of the body, we measure three types of densities. Which are the three densities? First one is called linear density of charge, which is measured in the case of, see, a thin conductor, thin. It can be a thin ring also. Can you see that? There is a ring, see, like this. A ring or a straight wire. So what do you mean by linear density and how to measure this? So linear density of charge is defined as, the symbol used for that, the symbol used for that is lambda. Linear density of charge is defined as charge per unit length. Charge per unit length, where the charges are uniformly distributed. So you can see on this entire conductor, the distribution is uniform. Okay. If the distribution is not uniform, then you consider a small length, dl, small length, if the distribution is not uniform, then consider a small length dl, in which the charges must be uniformly distributed. So in that case, we use the formula lambda is equal to dq by dl. If throughout the length, if the distribution is uniform, then we use q by l. If the distribution is not uniform, then select such part of the conductor where the charges are uniformly distributed, and then use lambda is equal to dq by dl. Q, dq, charge measured in coulomb, divided by length, meter, coulomb per meter is the unit of linear density of charge. So linear density of charge is used in the case of linear conductor or thin wires. We use this type of density. Linear, the word linear will tell you that we have to make use of straight conductor or a conductor which is bent in the form of a ring. Okay. Second one is called surface density of charge. Surface. That means we need a structure which is three-dimensional, and charges must be present only on the surface of it, and that can happen only in the case of conductors. So surface density of charge is used only in the case of conductors, because in conductors the charges will reside only on the surface, not inside the conductor. Okay. So how to measure surface density? The symbol for that is a sigma. So surface density of charge is defined as the charge per unit area, that S stands for surface area. Charge per unit area, where the charges are uniformly distributed. If the distribution is not uniform, for example, something like this, in this case the distribution is not uniform, then select a small portion, small portion of the area in which the charges are uniformly distributed, so that we can use sigma is equal to dq by ds. So for this type of conductor, I cannot measure sigma straight away because the distribution is not uniform. It is non-uniform. In such case, you have to use sigma is equal to dq by ds. What is the SI unit of it? The SI unit is coulomb by area, right? So coulomb per meter square. Coulomb, area is meter square. So coulomb per meter square is the SI unit of surface density of the charge. The third one is volume density of charge. See, this is used only in the case of insulators, non-conductors, because in insulators and non-conductors, the charges are present even inside. Okay, they are not only present on the surface, but they are present even inside also. So this is in the case of non-conductors. So that means I have to consider not only surface, but I have to consider this, even the space inside, correct, the conductor. So which means I have to consider the entire volume of the structure. So therefore, and the symbol used for that is rho, which is volume density of charge, is defined as a charge per unit volume, where the charges are uniformly distributed. And if the distribution is not uniform, then select a very small volume dV, in which the charges dq must be uniformly distributed, and the symbol is rho. It's a charge per unit volume, so it has to be coulomb per meter cube. Now, regarding surface density of the charge, suppose if I consider a sphere, okay, sphere. You consider a sphere of radius r, so r is the radius of the sphere, and q is the total charge distributed on the surface of the sphere. Then for sphere, I can calculate the surface density, sigma. How to calculate the surface density? Surface density is defined as charge per unit area, charge by, what is the formula for area of the sphere? Area of the sphere is 4 pi r square. So this is used only for spherical conductor. So for spherical conductor, sigma is equal to Q by 4 pi r square. So hope you have understood these three types of densities of charges. So linear density is used for straight wire or for thin conductors, and surface density is used exclusively for conductors only of again any shape, and volume density is used exclusively for non-conductors only. So whatever the topic that I have explained, revise it. So I am going to provide the notes, and then you have to start writing the notes of this particular chapter.